Let's be honest, the word calculus can sound a little intimidating, right? But what if I told you it's not some impossible math class, but a language that was invented for one specific purpose, to describe our dynamic, ever-changing universe. So let's dive in and learn to speak it.
You know, the math we learn first, like geometry and basic algebra, is amazing for a world that holds still. It's perfect for finding the area of a triangle or figuring out a trip at a constant 60 miles per hour. But our world, well, it doesn't hold still, does it? Plants are growing, rockets are accelerating, things are constantly in motion. These are dynamic problems. And for a long, long time, they were a huge puzzle. How do you even begin to describe something that refuses to stop changing?
So let's start with a classic question. Picture this. You're in a car and you hit the gas. Your speed isn't constant anymore. It's going up. Now, if I ask you what your average speed was over the last minute, that's pretty easy to figure out. But what about your speed right now, at this one single exact instant in time? That's the problem of finding an instantaneous rate of change. And that is the first major question calculus was born to answer.
Now, we actually have a tool for this from algebra, right? It's the average rate of change. You probably know it as just slope. For our car trip, it's simply the change in distance divided by the change in time. And that'll give you an average speed. Maybe you averaged 50 miles per hour. But see, that's the keyword, average. It doesn't tell you how fast you were going at any single moment.
So how do we get from an average to an instant? Well, the idea is just brilliant. We zoom in. We start by picking 2 points in time on our journey and calculate the average speed between them. Okay, now, what if we move those points closer together? Instead of 1 minute apart, what if they're 1 second apart? Or a half second? A millisecond? As we shrink that little gap of time, the average speed we're calculating gets closer and closer to the true, instantaneous speed at that one moment.
This zooming in idea is made mathematically official by this incredibly powerful concept called a limit. A limit is the value, the destination really, that you're getting infinitely close to as you shrink that interval down towards zero. It's the magic trick that lets us talk about what's happening at a single point in time, without ever having to actually divide by zero, which, as you know, is a big no-no. And that brings us to the first hero of our story, the derivative. The derivative is that instantaneous rate of change. It's the exact slope of a curve at one specific point. It's what you get when you take that zooming in idea all the way to its logical conclusion using a limit. It is the answer to our question about the car's exact speed at any given moment. Okay, so let's put that idea on hold for just a minute and switch gears to a totally different problem. This one stumped the ancient Greeks for centuries. You see, finding the area of a square or a triangle, easy. But what about the area of something with a curved edge, like a circle, or the space under a swooping parabola? How on earth do you calculate that precisely? Well, the legendary Greek mathematician Archimedes had this amazing insight. He imagined taking a circle and cutting it up into a ton of tiny little pizza slices. Then he imagined rearranging them, alternating them up and down. And when he did that, the whole thing started to look kind of like a rectangle. He figured if you could just make those slices smaller and smaller, it would get closer and closer to a perfect rectangle. And that is the core idea. We can approximate a weird, curved area using simple shapes we already understand, like rectangles. You can see it right here. If we only use 4 rectangles, the approximation is pretty rough. But look what happens when we use 8, and then 32. The more rectangles we use, and the skinnier they get, the better they hug that curve. The total area of all those rectangles gets much, much closer to the true area. Now, here's the big leap of imagination. What if we didn't just use a lot of rectangles? What if we could use an infinite number of infinitely thin rectangles? Can you picture it? They would fill that space perfectly, with no gaps, no jagged edges. If we could just add up the areas of all those infinite tiny pieces, we'd have our exact area. And that brings us to the second hero of calculus, the integral. The integral is the mathematical machine that does exactly that. It's the process of summing up an infinite number of infinitesimally small parts to find the total. It gives us the precise area under a curve, and more broadly, it represents the total accumulation of something over time. Okay, let's just pause here for a second. For literally thousands of years, these two problems, finding the instantaneous speed and finding the area under a curve, were seen as completely different things. They were developed by different people in different eras. I mean, one is about division and finding a slope, the other is about addition and accumulation. So what could they possibly have to do with each other?
The answer, which completely revolutionized science and math, is everything.
So here they are,
The two sides of our story. On one side, you have differentiation. That's the process of finding the derivative, the slope. On the other side, you have integration, finding the total area, the accumulation. They really do seem like total opposites, don't they?
And this is the climax, the fundamental theorem of calculus. It was discovered independently by Isaac Newton and Gottfried Leibniz, and it revealed this deep, hidden connection. It says that differentiation and integration are inverse operations. They undo each other perfectly, just like multiplication undoes division. It was this stunning link that connected the problem of slopes to the problem of areas and unified them into one incredibly powerful system.
And this wasn't just some neat mathematical trick. This discovery unlocked our ability to truly model and control the physical world. Think about it. Weather forecasters use it to predict storms by modeling changes in pressure. Rocket scientists calculate thrust as the derivative of momentum. Economists use it to find the exact point of maximum profit. And doctors can model the rate a tumor is growing to see if a treatment is actually working. It's everywhere.
And these applications get super specific. In business, for example, the derivative of a cost function gives you what's called the marginal cost. That's the exact cost to produce just one more item. So using a real-world cost model, the derivative can tell us that making the 401st iPad costs about $7.50. That is incredibly precise, actionable information.
And integration does the same thing for accumulation. If we know the rate that water is flowing into a tank, which might be changing over time, we can use an integral to find the total amount of water that's collected. In this case, by integrating that flow rate over 80 minutes, we find that exactly 4,000 gallons of water have accumulated. It sums up all those little changes to give us the big picture.
So we come right back to where we started, from the speed of an accelerating car to the area of a circle, from rocket launches to economic models. Calculus gives us the essential toolkit. It truly is the language that we invented to finally understand a universe that is always, always in motion.
So the next time you see a weather forecast, or watch a stock ticker go up and down, or even just feel your car accelerating, remember those two big ideas: finding the rate of change at one single instant and summing up infinite tiny pieces to find a whole. They're the two sides of calculus, the language that describes it all. Now that you understand this language of change, what will you see differently?